Okay, so that's the hour, so maybe we'll get started. Just quick couple of announcements before we get to the course material. So on Compass, you may have seen that I posted the announcement that we're recording the lectures, which is why I'm wearing this ridiculous earpiece, and we're hosting them online. And so if you miss a lecture or you want to catch up on some material or something, you can go to the link that's posted on the Compass website, and you can see all these lectures that have been hosted up there for you. The other part is, so I've posted last time the quiz for Module 1, and so Module 1 is Bash and MATLAB, and also the problem set, so the project for Bash and MATLAB, and so those things are all up there now, and so we're going to finish Bash today and get sort of 75% through MATLAB, but I would encourage you to start working on these things just now. So they're due in 9 days, they're due a week on Thursday. And so do leave yourself plenty of time to take a look at these, have problems, and ask me questions. So I'm available, right after class or during the office hours on Tuesdays. So particularly if you've never worked with Bash and MATLAB before, I would suggest you really do start early on these guys. And so just to take a look at the syllabus. So we are on lecture 3, and so it's September 2nd today, and these things are due on the 11th. So you've got over a week to take a look at them, but you have most of the Bash skills you need right now. You'll have all the Bash skills you need in about 10 minutes time. And so there's no reason you can't start working on the Bash thing and then, start working in the MATLAB after that. Okay, sound good? Okay, and so here's where we left off last time. Okay, so first of all, we were running through all of the Bash commands, giving you the vocabulary to be able to use Bash. And then I gave you on Compass a bunch of Bash scripts for you to download, and we were talking through those scripts. And the idea was that the scripts show you Bash in action, and also gives you sort of templates and a sort of basic examples that you will then use. You'll sort of hack these things into your project, and so you'll use these various idioms, these loops, these ideas in your project. And so we got up to stringer, so that was the last one we were looking at, and we were introducing sort of arrays and this magic thing, which sort of means all the arguments I pass to my Bash script. That's what that $@ means. And so before we move on to the last couple of scripts, are there any pressing questions that came up? So I know some folks had emailed me with some sort of elementary concerns, and so that was good that you're getting to use Bash and you're starting to find difficulties. But anybody have any questions right now they want to talk about? Okay, so then let's finish up the last couple of scripts, and then we'll move on to MATLAB very quickly. Okay, and so script 7 was known as filer, and so basically this was a sort of a silly script. It doesn't do something particularly important, but it illustrates a point very nicely. And so it's going to test whether user-supplied strings are files within the present working directory. And so what we're going to try and illustrate here are 3 concepts: the concept of an infinite loop, Control-C to break you out of an infinite loop, and reading user input. And so if you open up Filer in VI or LESS or Head or Cat or Notepad, whatever you prefer, you'll see we start with a shebang line. We've got our comment line, which we just discussed, and then we've got the body of the code. And so what is this code going to do? And so we start out with a while loop, and this is sort of a funny while loop because it's an infinite while loop. And we're saying that while 1 is not equal to 0, and so that's always going to be true. That's never going to change. It's not like 1 is a variable and 1 is a number. It's saying, is 1 equal to 0? So 1 is never equal to 0. And so this loop is going to go forever. And so that's usually a pretty dangerous thing to do. You never want to sort of have infinite loops, but we're going to use it for a very important purpose. And so immediately we're going to notify the user we're entering an infinite loop, and we're going to say echo to the terminal, please enter a file name to test, Control-C to exit. And so that's telling the user if you want to break out the script, it's not going to do it automatically. You're going to have to hit Control-C. And that's basically just a break command. And so Control-C on your keyboard will break you out of your Bash script. And so if you have a Bash script that's running wild and it's sort of causing all these problems, you can hit Control-C to kill the script. And so a very useful thing to be able to do. Okay, so nevertheless, we've entered the loop. Then we're going to use this read command. So this is reading user input. So read str. So whatever comes in through the keyboard is going to get stored in str. And so you're actually going to use this in your Bash project. This is going to be a very important thing you want to use. Okay, so now we've read some data into str. And then what we're going to do is test whether str is a regular file in the present working directory. So now we need an if loop, and we're going to say if, then open these square brackets, which is the test clause, -f $string. So $string dereferences string. So that was whatever I typed into the keyboard. And -f is just a sort of shortcut for saying, is this a regular file? And so there are a bunch of these things. -f is the file exists. It's not a directory. -e is the file exists. It can be a directory. -d is a directory. -r is file readable. Writable is -w. Executable is -x. So a bunch of things. Again, just vocabulary. So you can look at this and pick out the one that you need for your project. Bless you. But today we're just going to say, is this a file? If this clause is true, then we have our semicolon then. So this is the if idiom. Then we go through and echo to the screen $str. It's double quotation marks, so we're going to dereference this. If it were single, it would actually print to the screen $str. That's not what we want. We actually want to see what lives in here. So $str is a regular file in the present working directory. Otherwise, echo $str is not a regular file in the present working directory. Then we close out our if loop with fi, and then we echo a blank line to the screen, and then we're done. And so once we hit this part, we're going to immediately circle back around to the beginning of the while loop, because this is an infinite loop. And so what does this look like in practice? Okay, so here's an example. I'm in a particular directory. I hit ls. There's a bunch of stuff in this directory. Then I'm going to hit filer, so I'm going to execute it. So /filer. Please enter a file to test, Control-C to exit. I type summer. It says summer is a regular file in the present working directory. Great. Then we go back to the beginning of the loop. Then I type winter, and it says winter is not a regular file in the present working directory. So it's just testing various things that live in here and see whether or not they're a regular file. Yeah, question? So this, well, what's your guess? What do you think will happen? Do you think it will work, or do you think it will not work? Right. So what's going to happen is you're going to type something into the keyboard, and so you type maybe 3 things separated by spaces, and then hit enter. And those 3 words separated by spaces are all going to get stored in str. And so then when it tries to find out if that is a regular file, it's going to have word, space, word, space, word, and that's not going to come up as a regular file. So you need to write a much smarter code to allow multiple inputs at one time. And you could do that. You actually have the tools to do that, because you could use something like, just jumping back one slide, you could dump everything into an array, and then you could sequentially text all the elements in the array. And so you could actually stick together stringer with filer and do exactly what you're asking. This one is dumber than that, and so it just does one thing at a time. Good question. Yeah?
So for the array, so we use the dollar sign and the attribute, so does that mean that you can put as many things as you want into your array?
Exactly. And so the default behavior for $@ is take everything that I enter, and it's delimited by a space. And so every chunk.
Every time we put a space, it knows that it's a new array.
That's what $@ expects. Well, not a new array, a new element that will be stored in an array. That's right. Yeah, very good. Is there a question over here? Okay, so that's so much for filer. And so you're definitely going to need to use the read command in your scripts, and you're definitely going to need to use if and while loops. And so these things are going to be very important for you. And probably you're going to need to use an infinite while loop for your project. That's one of the suggestions, at least. Okay, so let's look at our very last script, which is square. And so what we're going to illustrate here, we're going to illustrate sort of iterating. So somebody asked before, what if I don't want to just iterate over the elements of an array? What if I want to have an iterating loop variable that goes 1, 2, 3, 4, 5, like a loop counter? So we're going to show that here. We're going to illustrate functions, which is sort of a very concise way. If you use a function a bunch of times, maybe you don't want to rewrite it every single time in serial in your bash script. So maybe you want to write it up front, and then you just call that function. So that can save a bunch of typing. And also the sleep command. So that does exactly what you would expect. It makes the system sleep for a certain amount of time. So it gives like a pause in the code. Okay, so let's look at square. So shebang line. Then we're actually going to hit some function declarations first before we get into the body of the code. And so let's forget about that for 1 second. First, let's look at the comment line. So it says print square of every 8th number between 56 and 107. So maybe that's something you're interested in doing. I can't imagine why. But again, we're just trying to illustrate a point. So we're setting up the iterative loop. And so we're going to start at 56. We're going to stop at 107. And our step is going to be 8, because those are the only numbers that we care about. Okay, so then we're going to start to enter our loop to do exactly what we request, which is to print the square of every one of those guys. And so we start with I is equal to $start. And so we're assigning the variable $start, which in this case is 56, to the loop variable I. Then we're going to hit our while loop. And the while loop does the following test. It says when $I is less than or equal to $stop. And so while this loop variable I is less than 107, the loop is going to execute. So we're going to run through the loop. We're going to assign the variable I2 equal to square of $I. And so we've enclosed this in those special funny primes, which means execute this bit first. And so we're going to execute this statement first, and then assign its output to I2. So what the heck is square $I? This is actually our function. And so what we've written up top is a function to do this squaring operation. So Bash doesn't have something like this built in. You can do it various ways, but there's no function call called square in Bash. So we're writing our own one. And so function square is basically just like a second Bash script nested inside your first Bash script. Maybe that's the simplest way to think about it. And it behaves exactly the same way. And so we define this. This is the idiom function square, open, close, curly brackets, open, close, regular brackets, and the special curly brackets hold the statements that we want to actually execute. And it behaves in exactly the same way as a regular Bash script, and you can pass it parameters. It's expecting things like $1, $2, which you'll remember this is the first argument you pass to it. This is the second argument you pass to it. So it's exactly the same way as a regular Bash script. Or indeed, it can operate without any arguments, and it could just dump some variable, hard code a variable into it. But it's more useful to expect arguments. And so this guy, this $I, is going to take the place of $1 when we pass this up to the script. So it's just like executing a second Bash script. Okay, so we hit square $I. So $I is going to start life as 56. It's going to come into this function as $1 equals 56. And we're going to do Z is equal to special prime symbol to make this execute first. EXPR, which is our integer arithmetic engine that we talked about before. $1 times $1, and then we're going to echo $Z out. So coming into this is 56. Coming out of this is 56 squared. So of course we could have just written this part directly in here, but we're trying to illustrate the concept of a function. Is that clear to everyone? It's a little bit subtle if you're not sort of familiar with programming. It's basically trying to nest one program inside another. Maybe it's the simplest way of thinking about it. Yeah. Right. And so in the same way, we don't have to declare what variables a Bash script expects. It sort of expects these things by default. This little nested program also expects these things by default. Exactly. That's right. That's right. Any other questions? Okay, and so what's happening now is we're assigning I2 is going to be 56 squared, and then we're going to echo to the screen $I times $I is equal to $I2. Then we're going to sleep for 1/2 of a second to allow us to sort of read the output. And then we're going to do this very important part here, which is just loop bookkeeping. So it's not actually doing anything oriented towards our program or squaring of numbers. It's just incrementing our loop variable. And so I now goes from EXPR $I plus $step. And so it's going to be 56 plus 8. And so we're going to increment this up to 64. And so the next time we roll around this loop, we're going to be squaring 64. Okay, so that's the script. There's a few things going on. It's not a super simple script, but it's a very nice script in that it's illustrating lots of very clean ways to do some programming. And so let's see if it works. And so let's execute square. And so if you do this right now in your terminal, you should see it will say things like 56 times 56 is equal to 3136. Then there'll be a 1/2 second pause, and then it'll do 64 squared and so on all the way to 104. And then it tries to do 104 plus 8, which is 112, and that's greater than our stop variable of 107, and so it's not going to execute that, and the program is going to terminate. Okay, so any more questions about squarer? Yeah. The previous one? Okay, so any questions on squarer? Yes, so let's get to filer in 1 second. Squarer. So it dies as soon as the Bash script dies because it's hidden inside that script. They also die, that's right, yeah. Yeah, good question. Okay, so file it. Yeah, so your question on file it. So so it's good questions. There's two ways of getting variables or parameters into a script. Number one is directly by passing them as arguments. And so you would do, say, /summer, and then your script is hard-coded to expect 3 arguments, so 2 integers and an operator. So that's the way you've designed the script. It takes 3 arguments and it operates on them to make its output. Another way you can get parameters in is to place read statements inside the body of your script. And so the script will stop here and it will expect something from the keyboard. This is like giving it parameters on the fly. So it depends which one is more useful to you. Perhaps if you're sequentially executing things and you don't know how many things a priori you're going to execute, maybe you want to use a read, because then you don't have to define a fixed number of parameters at the beginning. But of course, you can circumvent that by using an array. And so an array is sort of another flexible way of including however many parameters happen to be passed. So it's really your choice. It just gives you a little bit of flexibility. Good question. So anything else on these scripts? Okay, so like I say, I don't sort of expect you to be able to reproduce these scripts in sort of a dark room with 0 resources, but if you can understand them, then that's really the point of them. And then the project is going to allow you to sort of take parts of these and use them in your own work. Okay, and so the last thing I want to discuss is this other special engine that you can access through Bash script called awk. And so some of you may know that an awk is a bird, so Unix and Bash and Linux like puns a lot. And so they like to have things with puns, and so this happens to be a bird. It also happens to be which is where it actually came from, is the first letters of the last names of the 3 people that designed it. So it was designed at Bell Labs by Aho, Weinberger, and Kernighan. Kernighan currently teaches at Princeton computer science, and so that made the programming language awk. And so it started life actually as a legitimate programming language, but now it's actually typically used as sort of an engine underneath Bash to do text processing. So if you want to do text processing, you can write a Bash script and then call up the awk engine to do all this nice processing for you, and then quit out of awk and return to your Bash script. And so it's used very, very frequently, which is why I'm introducing it right now. It's powerful, simple, fast, and flexible, and it comes with almost all Linux distributions for efficient line-by-line text processing. So actually there are some programming programs, or sort of programming courses, I should say, around the country which actually teach programming using awk. And so it really is a programming language. But I'd like you to think of it more as just a text processing tool. Okay, so if all it does is text processing, maybe you don't care about it. Maybe you're just going to use VI or Emacs or Notepad. And so that's fine for small tasks, but at scale, this really is not going to be sustainable. And so imagine I asked you to extract the 3rd column of every line of a 50,000 line text file. So doing VI or Notepad is just going to be extremely tedious and painful, and you're going to make mistakes. Or perhaps you want to divide the 2nd field of each line by the 7th field and save the results in a different file format. Or extract every 15th line of this file and invert the field ordering from last to first. So again, these are all very painful things to do by hand, but very simple to do in awk. And so there is some activation barrier, some overhead to getting used to awk, but as soon as you master some very basic syntax and vocabulary, you can do exceedingly powerful things like this with basically 1 line of code. Okay, and so it integrates seamlessly into Bash. You can actually use it directly from the command line, or you can put it into your Bash shell, and it's simply the right tool for a lot of text processing jobs. So we're barely going to scratch the surface of awk, and actually a sample program I'm going to give you is going to be enough for you to sort of hack it into your project and use almost the most basic thing you could possibly do with awk. But it goes very deep. And so this is actually a nice tutorial that's online, and so if you're interested in seeing the more advanced features of awk, I would recommend you take a look here. It's a very nice introduction. And so what does an awk program look like? And so imagine you have your Bash script, and so you have your shebang line, you have your comment line, you have a bunch of stuff that Bash does, and then inside your Bash script, you boot awk, and so you call an awk engine up. And so it looks like this. The first line says awk, then you open with a single quotation mark, capital letters begin, curly braces. This does a bunch of stuff before the program really gets going. Then another pair of curly braces, this is the body of the program, then end, and a final pair of curly braces, and this is what the program does before it quits out. So frequently these guys are empty. Frequently you don't need it to do stuff before and after. You just want the program to run as you design it. So sometimes only these will be full, and this will just be open brace, closed brace with nothing between them, and that's fine. Okay, then you finish with another quotation marks. You have to close out your quotation marks. So everything outside the quotation marks is Bash. Everything inside the quotation marks is awk. Okay, so that's important. And then you have the in file, and then you dump stuff to the out file. And so this is the file awk expects to read, and this is the file awk expects to write. And so as we'll see in a second, you can actually read stuff from the terminal and write stuff to the terminal, but this is the canonical way of doing things. You take an in file and you write an out file. Okay, and white space doesn't matter, and so you can have as many spaces or whatever within the body of the code, and it will still work just fine. So just before we get onto awk, imagine you don't have files, but you actually want to get an input from the terminal, and so you could cat or head an in file, and then you could send it to awk. And so it's another way of sending awk input, rather than have in file written here, is actually to grab the in file in the terminal and send it directly to awk. So it's less common. Similarly, you could omit the out file and the output of awk. So if you omit this, then the output of awk will dump directly to the terminal. So again, less common, but you can do that if you want. And then we've talked about this previously, if you don't want to overwrite your file, but rather append to your file, you replace the single greater than sign with a double greater than sign. This means write to the end of my file rather than overwrite my file. And so you've seen this in the context of bash. It's just the same in awk. Okay, so that's sort of just setting up the awk program. So how do we actually write the awk program? So what goes in the curly braces? So the right way to think about awk is it performs line-by-line text processing. So it's going to go through your file one line at a time, and it's going to do the same thing to every line. That's just the way the program is designed. That's a common thing you want to do. And so that's the right way to think about it. Okay, you have to assign internal variables. You need loops. You can actually pull in bash variables from the surrounding script. And so we said it was bash, 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 awk, quotation mark, then it was awk. So that's the awk stuff there. Close quotation mark, we're back to bash. So you can actually pass things from bash into awk. And we'll show that in 1 second. You can print the terminal or file, and awk can do some basic arithmetic. So this is the most important thing. Think about it processing a text file line by line, and you can pull in bash variables from the surrounding bash script. Okay. Okay, so let me illustrate this by an example. I realize this is all very abstract now. This is going to be the most complex example that we do, so I recommend you take some time to take a look at it at home. But this is the setup. So imagine that we have a PDB file. So if you do any biophysical simulations, you'll recognize this is a protein data bank file. So it holds the coordinates and some information about a protein. That's not particularly important for our purposes. But what I want you to do is take this PDB file, which comes in a standard format, and every line contains the XYZ coordinates of that protein atom, plus a bunch of other junk, like its charge, its mass, its name. Imagine I only wanted the XYZ information. So every line, I only want XYZ. And I want you to extract that into these new files called coords.txt, just containing the XYZ information. So we're going to take peptide1.pdb and print out the XYZ information into coords1.txt. So that's the idea. So you could do this by hand. I want you to do it using awk. I then want you to take these 3 files and concatenate them together into this coords_concat.txt. So we take coords1.txt, right below it we put coords2.txt, right below that we put coords3.txt. So this is like your brief. This is what I would like you to do. So we're going to use bash to iterate over the files, and we're going to use awk to do the text processing off each file. So that's the plan. So this is what peptide1.pdb looks like, and again, this is available on Compass or from that link that I gave you last time, so you can download and take a look at this. And so we have some header lines, we have some information about each atom, its atom number, its type, the residue it belongs to, and then here's the XYZ data, and here's some other information like its charge or its B numbers, etc. So the thing we're interested in is here. And so if we were trying to do this with Notepad, we would have to open it, we would have to highlight this line, dump it into a Notepad file, and do that repeatedly for every atom in the protein. So that'd be a huge headache if you had more than, say, 10 or 12 or 20 atoms. It would just be a big pain. So let's automate it. And so this is the output that we want, which is every line, these 3 fields have been printed. So everyone clear on what we would like to do. Okay, so how are we going to do it? Let's look at the script. Okay, so this is the awker script. We get our shebang line, so we're going to start with bash, and eventually we're going to call awk, so the awk call lives down here. All the way up to awk is just regular bash. So we're going to extract XYZ coordinates from PDB files. First of all, we're going to set up the file iteration. So we're going to have an in-file name is peptide. The in-file suffix is PDB. And so this is setting us up to run through files with names like peptide something.pdb. The out file name is going to be coords. The out file suffix is going to be txt. And then we're going to use a loop to go from 1 to 3. And so we're going to start at 1, we're going to stop at 3, we're going to set by 1. So this is going to allow us to look at peptide1.pdb, peptide2.pdb, peptide3.pdb. And so clearly you can see that this can scale to any number of files very efficiently just by changing this value. Okay, then we're going to do a little trick. And so we're going to initialize the concat file. And so we're going to say, does there exist within this current directory something called, and this out file is going to be coords. So this is going to dereference to coords, underscore concat dot, and then the suffix is txt. So this is asking, is there a file in the current directory called coords underscore concat dot txt? If there is, we're going to remove it because we want to clear that out because we're going to make a new one. So we're going to delete it, and we close our if loop, and then we're going to touch this file to start a brand new copy of it. So you can imagine doing something differently. Maybe you don't want to remove it. Maybe you want to move it to the trash can, or maybe you want to rename it or something like that so you don't delete it forever. Right now we're going to delete it forever. And remember, this is an irrecoverable operation. So be very sure of things when you're using the rm command. Okay, so up to here we've set up our loop, and then we've set up our file that we're eventually going to concatenate everything into. So let's actually iterate over the files. So very similar to what we just saw, we start up our loop variable I with $start, which is going to be 1, and then we're going to enter this while loop, which is going to be while $I is less than or equal to $stop. So while 1 is less than 3. And let's jump to the end of the while loop so we can see that we're incrementing things by our set, which is going to be 1, and done. Okay, so we've not talked about the body of the while loop, but you can see the structure of the while loop is exactly the same as we saw before. We're doing I equal 1, 2, 3, and we're going to do something with that. Okay, so what's the something? So before I discuss this, is everything else clear on the script? Any questions about it? I think we've seen everything before. Okay, so let's look at awk. Okay, so let's pop awk. So awk, apostrophe, open braces. So you can see at the begin double braces and the end double braces are absent because we don't need them. We're not going to do any of that stuff. So we just have the regular braces with the awk code inside it. Okay, so we're going to awk through each file in turn. And so which file are we actually going to look at? The file we're going to look at is $infile_name, which is peptide, $I, which is going to be 1, $infile suffix, which is PDB. So every time we run through the loop, we're going to look at a different file. And we've enclosed all this stuff in double quotation marks to make sure that bash knows that it's all together. So it's going to be peptide1.pdb. And what we're going to output to, we're going to output to coords1.txt. That's the infile and the outfile that awk is expecting. So because these two statements occur after we've closed out the awk loop, this is just regular bash. So it's just normal bash right there. So we've seen that before. So we've told awk what infile to expect and what outfile we want it to write. Now what do we actually want it to do? And so we said we want to print those 3 fields. And so if I go back one slide just for a second, we want it to print X, Y, and Z in every single line. And so the way we get it to do that is, first of all, we say, let's look at this part, print F, and then this is awk code now, this is not bash. Print F just means print. So if you use MATLAB, you'll be familiar with print F. So it just means print in a formatted way. How are we going to format things? You have to open and close with double quotation marks, and then provide the formatting variable for each output that you want to write. And so %8.3f means I want to print a float with 8 characters and 8 digits consisting with 3 decimal places. So there's going to be 8 digits in all. The last 3 are going to be beyond the point. And so it's going to have 3 decimal places of precision. And I want you to print that 3 times. And so that's the output. That's going to be the X, Y, and Z coordinates with 3 decimal places of precision. And what do I want you to print? Then there's a /n, which just means new line. That's just a new line character. And what do I want you to print? I want you to print $6, $7, and $8. So we're inside awk here. So these are not the bash arguments. These are awk arguments. So when awk sees a new line in a file, let's go back one slide. So awk starts to roll through these lines. Every field separated by white space is a new code. And so this is $1, this is $2, $3, $4, $5, $6, $7, and $8. So 6, 7, and 8 are the ones that we want. Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8. So it's annoying. It's unfortunate that $123 refer to bash arguments and sort of fields within awk. It's confusing, I admit that, but you just have to get used to it. So when you're inside awk, $123 refers to the fields in a particular line of a file that you're reading. Okay. So we just want to print these 6, 7, 8 to our output file in this formatting. So floating point, 8 digits with 3 decimal places. Okay, then we saw this part before this call, before the printf statement, which says if nr is greater than 5 and nr is less than 16. So what the heck is this? This is saying if the number of records in awk means the number of lines that I've read, is greater than 5 and less than 16, I want you to do this. Otherwise, don't do anything. And so why do we need that? Well, in your PDB file, there's actually 5 header lines. And so we don't want to do anything to those lines. We just want awk to ignore them. And so until you are greater than the 5th line, awk does nothing. Then once you get greater than the 5th line, then it starts to analyze this data, and then only analyzes it down to the end, down to the final one. Because when we said when you're less than 16, stop doing whatever I told you to do. Okay, so the two things I want to illustrate here, which are super elementary, but the only things you're going to need for your project, are how to tell awk to skip lines using this number of records, and how to print things in a particular formatted sense. And so you can just Google awk, or you can go to that programming guide and see how you can print things with different formats. You can print them as integers, or floats, or scientific precision, things like this. The one that you're going to need is floating point. And so that's going to be the percent something point something f. That's all I want to show there. Okay, so question? That's right. That's what awk expects. You need to give it its formatting statement, how you want to print them, and then what you actually want to print. You need to describe them all, I believe. Yes, you need to, your number of format statements needs to match the number of arguments. Yeah. And I'm not sure if awk is smart enough to complain in a reasonable way and tell you these mismatch. It may just make a mess. Yeah. So there's this 8 right here. So let's look at the output. This is the output of the awk script. And so if you count the number of spaces, you'll see there's, for each field that we've printed, you'll see there are 8 spaces it takes up. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, and the last 3 are beyond the decimal point. And so it just gives you the space. And so you need to make sure that your first number is big enough to accommodate the second number. So if you ask for 8.52, it'd be a huge mess. So you just need to be careful about that. Okay, any more questions on the script? So, like everything, the best way to understand it is to run it yourself and to sort of mess around with it. Yeah. So awk has some built-in arithmetic. So one of the goals of the project is for you to figure out yourself by going to that tutorial. The link that I gave you is how awk can do internal arithmetic. And so it's very similar to the way that bash does arithmetic. You can just multiply one number by another. Actually, it's even simpler. So let me give you a hint. The way you would actually do it is in this field here, instead of having, say, $6, you would have $6 times $8. And that would multiply field 6 by field 8. So it's actually super simple. So awk can do some basic internal stuff like that. Okay, and then the last line of the, okay, so then we're done. Okay, and so the files look like this, and so you're actually able to, okay, so sorry, I missed something. So right here, so we've printed peptide1.pdb to coords1.txt, and then what we do is that we cat, so we read coords1.txt, and we append it to the concatenation file, so coords_concat.txt. So we just take all that stuff, and we add it to the end of coords_concat.txt. And we do that for each one of the 3 files. And so we have an individual file corresponding to each PDB file, and we have one sort of agglomerated file with all the XYZ data all dumped together. And so then if you look at the final coords_concat.txt, it looks something like this. And so the first 10 lines came from peptide 1, the next 10 from peptide 2, the final 10 from peptide 3. So why you'd ever want to do this, I don't know, but I'm just trying to illustrate a point for you. Okay, so there's quite a lot going on in there, but the real thing I want you to sort of understand, we're really just scratching the surface of awk, is this number of records idea that allows you to skip lines and printing stuff in a nice formatted sense. And so you can actually go a long way with awk, just having those two things. Okay, so that's it for bash. So any bash questions? Okay, so we're going to start on MATLAB. So let's just take 2 minutes break. If you want to grab some water, use the restroom, and download all the stuff from Compass pertaining to MATLAB. And so there's sort of the lecture notes, and there's also this weird file called like water.csv. So make sure you have that because we're going to be using that in just a second. Okay, so 2-minute break. Okay, so that's 11:40, so maybe we'll get started on MATLAB. So I know everybody filled in their sort of surveys, but can I just have a show of hands again for who's used MATLAB before in any sort of capacity? Okay, great. So it's around 50-50. So the reason we're doing this is to get everybody up to speed with MATLAB. We're going to be using it to process output from all the molecular simulation and quantum espresso and phase equilibria codes we're going to be using. And so if you've never seen MATLAB before, don't worry about it. This is the purpose of this module. Okay, so what is MATLAB? So MATLAB stands for Matrix Laboratory, and so basically it's a mathematical engine that can do a bunch of arithmetic, it can do some curve fitting, it can do optimization. Everything you could possibly ever imagine to do mathematically is probably in MATLAB somewhere. And it's called Matrix Laboratory because the way it expects data and sort of handles data is in arrays like matrices. And so, vectors, matrices, multidimensional matrices. That's typically the standard container by which MATLAB expects data to come in. Okay, so you can do data analysis, financial modeling, bioinformatics, visualization. You can even do symbolic math. And so if you have some crazy integral you don't want to do by hand, you can actually convince MATLAB to do it for you. It won't always give you the nicest answer, but it will usually give you an answer. And sort of modeling platform. Programming language, you can program very nice scripts to do reasonably powerful stuff in MATLAB. But perhaps it's most elementary, you can think of it as sort of a numerical calculator. Okay, so Wikipedia describes it this way: a numerical computing environment and fourth-generation programming language developed by MathWorks. That's probably sort of an empty statement, but it basically does all the stuff that I just said. It was initially developed at the University of New Mexico in the 1970s. It's now a for-profit commercial enterprise developed in Natick, Massachusetts. They like to hire engineers, and so if you're sort of interested in this sort of thing, MathWorks are usually hire a good number of folks every year. And so why do we use it? Well, perhaps the sort of flippant answer is because it's here. The university pays for a site license, and so it is a software package we can use. We could have used Mathematica or something like this, but MATLAB is pretty prevalent both in academia and industry, and so I think it's a useful thing to learn, and it's available to us right now. It's a powerful interpreted language, which means that you sort of type stuff, and MATLAB does it. So we don't have to sort of code it in some crazy way like C++ or Fortran. We can just type commands and they'll be executed, similar to Python, if you're familiar with Python. So it's an interpreted rather than a compiled language. So with Fortran and C++, you have to write your code, you have to compile it, and then you have to run it. With MATLAB or in Python, you can just type stuff directly and it will execute. So it makes for doing things very quickly, and you can do very quick sort of data exploration and analysis using this. So for example, in my laboratory, if we're working on a new code to try and do something new in sort of molecular simulations or perhaps some data analysis or machine learning, I might very quickly prototype the idea in MATLAB or Python, and then once we're confident that the algorithm actually works and is going to do the job we want, then myself or one of my graduate students might put it into like C++. So we get the speed ups from C++. You can get like orders of magnitude faster execution, but it's just much more painful to do. So for exploratory analysis, MATLAB is great. It's really well documented and its interface is excellent in my opinion. And there are a bunch of really powerful toolboxes, many of which the university subscribes to. So if you want to do bioinformatics, you can pull down the bioinformatics toolbox and do some really cool stuff with that. Visualization, optimization, all these things are available to do. You can make publication quality graphics. So all the papers that we publish, we typically make the figures in MATLAB. You can sort of endlessly customize them, and they look really good, much, much better than Excel. And it has this nice blend between simple interfaces, but you can actually access everything under the hood. And so you can look and see what MATLAB is actually doing under its optimization toolbox and modify it if you so wish. And it's freely available as a site license to UIUC. You do need internet access and a VPN connection to use it off campus, which is a little bit of a pain. You can't sort of run it offline, but it's pretty good. Okay, so I've sort of promulgated why I like MATLAB. Why might you not like MATLAB? It's an interpreted language, so it's very slow. But MATLAB is sort of aware of this, and there's a way to get around it. You can actually write MATLAB code and compile it, and that makes it execute a lot faster. So that's not something that we're going to do, but I think it's important to be aware that you can actually compile your MATLAB scripts, and that allows them to execute sort of, 2, 3, 4, 5, maybe 10 times quicker than the regular script that you would write. So a nice feature. Okay, well, what about if you don't like MATLAB, you hate MATLAB for some reason, you don't have access to MATLAB, what else could you use? You could use things like Maple, Mathematica, or IDL. These are all sort of MATLAB competitors. Mathematica is probably the most mature. Actually, I think MATLAB bought Maple, so it's really MATLAB. There are some open source alternatives, so GNU Octave. Python has sort of a Scilab, and then there's FreeMat. And so these are sort of alternatives one might think of using. If you're not at some university that has a site license, you could use these things. In a pinch, this thing is great. It's actually an online utility that runs GNU Octave, and GNU Octave syntax is almost the same as MATLAB. And so if you're somewhere and you don't have MATLAB for some reason, you can actually navigate to this website and actually execute some MATLAB stuff there. It's not super efficient for large tasks, but in a pinch, it can be a nice thing to do. So conspicuous by its absence is Excel. So can I use Excel? No, not in this course. Why? That's the short answer. The longer answer, it's really a goal of this course to develop some competency in scientific softwares, one of which is MATLAB. And so I'd like you to get familiar with MATLAB if you're not already. And all the analyses and the plots as part of the homework are expected to be done in MATLAB. And so if you get an Excel plot, you're going to take a hit on that, I'm afraid. And so please just make it in MATLAB. It's one of the things I want to convey to you is how to use MATLAB and get comfortable using MATLAB. So go ahead and do that. So what's the real answer? The real answer, the Excel is a really awesome tool for quick and dirty analysis. You have a bunch of data, you want to very quickly put a line through it, do a linear regression, and make a sort of messy plot. So that's fine. Excel is great for that. But it really lacks the mathematical firepower for sophisticated analyses, and we're going to illustrate some of these analyses in this lecture. The analyses are less efficient and clunkier. If you want to reanalyze something, you typically have to start from scratch, and so you have to right-click and do all this crazy stuff all over again. If you write a MATLAB script very cleanly the first time, it's very, very easy to modify down the road. And the graphics are not publication quality, so you could spend a whole weekend trying to make an Excel plot look nice, and you could generate an equivalently nice MATLAB plot in about 30 seconds. And so it's really valuable for visualization. So that's the real answer. Okay, so what are the basics of MATLAB? So let me just introduce to you MATLAB as if you'd never seen it before. So it's a high-level interpreted programming language. And so basically you're going to get a terminal that looks a lot like Bash, but a lot fancier. And so you're going to open MATLAB, you're going to get your command prompt. So there's going to be a lot of nice GUI stuff around it too. And so it's a commercial thing. They're trying to make money from it, so they want it to be nice and user-friendly. And it really is. It's done a very nice job. And so the main way to interact with MATLAB is to type text into the command line. So you type MATLAB commands in here, and they execute, or to write scripts, similar to Bash scripts, except they're MATLAB scripts, containing a bunch of commands that you can then run from the terminal. So you write a MATLAB program, and so then you execute the program from here, and all the commands inside the program sequentially execute. So in that respect, it's quite similar to Bash. And scripts terminate in .m. And so when you have a MATLAB script, sometimes they call them a MATLAB function. There's a subtle difference between the two we're not really going to worry about. They all terminate in .m, and so that's just the file suffix for MATLAB scripts. So the interface kind of looks like this, and so you have your command prompt here where you type your commands. There's some menus up here where you can operate. These are sort of your current working directory, so this is all the files that you currently have available to you, and these are all sort of the variables that are currently active in your workspace. So if you've loaded variables, they will appear here, so that's a nice feature. And then you have your command history, so all the commands you recently executed. So you can hit the up key, just like you can in Bash, and sort of cycle back through all these commands that you've previously executed. So that can save you some time. What does a script look like? So this is sort of a MATLAB script, since I just opened it in the native MATLAB editor. So if I go back one slide for a second, you can go to File, Open, or Edit. I think it's in File, Open, and open a script. And MATLAB has its own built-in editor, so you can start editing the MATLAB script sort of natively within MATLAB. So this is nice because there's all these nice sort of highlighting of comments and highlighting of commands. You could, of course, edit it directly in Notepad or indeed VI. That would be fine, but it's actually nice to edit stuff directly in MATLAB because of all these nice features. So this is a MATLAB function because it starts with the word function, the function name, and then an argument list. And so you can think of this as sort of a sealed black box. And so you call the function with the argument, stuff happens, the function quits, and all the variables die. So that's why it's a function. It's like it's sealed off from the rest of MATLAB. The only way to get stuff into it is by passing it variables or using the read command, just like in Bash. A Bash script does not have this line at the top. It's just a list of commands. So a script is just like if you typed all the commands into the terminal and executed them one after the other. So it's not sealed off from MATLAB proper. All the stuff that's active in your workspace is available to the script, and all the stuff you sort of make in the script is then live in the workspace after the script finishes. So it depends what behavior you want. I tend to use functions because I like to have stuff sealed off. Other people prefer to use scripts just because it's easier to interact with the workspace. You can load stuff into the workspace, run the script, and the script can operate on those variables. You don't have to explicitly load them into the function. So just whatever you prefer. And the way you'll figure out what you prefer is just to do it and get comfortable with it. Okay, so you're off campus, you don't have MATLAB on your computer at home. You can download it from the U of I web store for free, I believe, so I recommend you do that. But if for whatever reason you want to use MATLAB on these EWS machines, you can actually SSH in and use them. And so you can do the remote login. So I would do SSH from my Bash terminal on my local machine at home, als@remotelinux.ews.illinois.edu. I would get a tunnel that went through, and then I would type in my tunnel MATLAB -no desktop -no display, and I would get something that looked like this. And so it would be a MATLAB terminal, but it's just the terminal. It's like the bare bones thing. There's none of the nice GUI associated with it, but this is legit MATLAB. So you can write all the MATLAB commands, and they will execute on an EWS server somewhere on campus. If you really want the GUI, you would open your SSH tunnel with the -Y, which allows for graphic forwarding. It's known X forwarding. And if you have a fast connection, you can then just type MATLAB, and on your computer at home, you'll get the beautiful MATLAB GUI and all the nice stuff that we just showed in the last two slides. Typically, I have a reasonably fast connection. You might have better ones. It's sort of painful to operate because everything runs so slowly because the graphics are coming through this SSH pipe. It's sort of too slow to actually do anything useful. But it depends on your connection speed. So if it doesn't work, don't worry about it. Most things you can do just using the command line. But the best solution is really to install it locally, and there's no reason not to because it's free. Okay. So the MATLAB ethos is sort of simplicity and versatility. So it wants to abstract everything as much as possible. And so it wants to put all the dirty stuff that you have to do to get any sort of hardcore scientific analysis under the hood and just sort of bury everything in a simple one-liner command. And so I think it does a very nice job of that. It's naturally based around vectors, matrices, and tensors. So the way you sort of store and operate on data or in these data structures is just a natural environment for MATLAB. There are other data structures, but these are sort of the most important ones. It's weakly typed and dynamically typed. So if you're a computer scientist, you may have seen these before. So weakly typed means that the type of your variable can change on the fly. So you can start out life defining a equals 36, and a will start out life as an integer. But then if you want to convert it into a float, you might multiply it by 3.2, and a would suddenly become a float because it needs to be upgraded because you've multiplied it by 3.2, which is not an integer. And so floats can turn into integers, integers can turn into floats, floats can turn into vectors. So this can be good because it allows you to do things very quickly, or it can be bad because it's sort of things are changing without you really controlling it explicitly. So this was a decision that was made by MATLAB because it makes things simple to be weakly typed. C++ is the opposite. You need to define something as an integer or a float, and it remains that forever. If you try and change its type, C++ will freak out. Okay, so it's just MATLAB's decision. A dynamically typed just is sort of bolted onto this, meaning that things can change on the fly. This means things can change on the fly. This means that things do change on the fly. You can build structures and classes, so if you like object-oriented programming, MATLAB does support that. Most things that I do are simple enough, you can just do it serially, sort of sequential programming, but if you like object-oriented stuff, you can do it. We're not really going to talk about that. There are millions and millions and millions of built-in functions to do lots of cool stuff very efficiently, but you can also write your own functions. So if you write your own function to do something, like squaring a number, like we did in Bash, you can just save it in an M file, and then you can call that function to do whatever you want. All the built-in functions are actually just MATLAB functions. They're stored in an M file somewhere on your computer. And so you're just calling functions that somebody else wrote in Natick, Massachusetts. And then you downloaded it onto your computer. And it's got very powerful scripting and visualization interfaces. So that's our, the 30,000 foot overview of MATLAB. No nuts and bolts yet, but does anyone have any sort of questions, general questions about MATLAB? Or general opinions? Do people tend to like MATLAB? Or are people scared of MATLAB? Okay, I'll take your silence. Okay, we got thumbs up. Very good. So actually, I think I said this before, but at the end of the course, when I sort of administered the final survey, a lot of people said that their favorite part of the course was actually learning MATLAB properly. They never had sort of formal instruction in MATLAB. So having some formal instruction, people seem to really like. Okay, so bear that in mind as we go through these slides and you start to hate me for showing you all this horrible, horrible stuff. Okay, so what does MATLAB do? So if you want to open a MATLAB terminal right now, if you've not already done so, you should be able to get to it on your Linux terminals. Yeah, so applications menu, EWS software, and then MATLAB. Okay, there's a bunch of other stuff in there. But I don't think there's a shortcut. So you could make a shortcut if you like. Okay, and so you can sort of follow along and do some stuff. This is super elementary. If you've never seen it before, I advise you to do this. And so you can use it as a calculator. And so 10 plus 17 should equal 27. And so MATLAB got that right, which is encouraging. So you can do simple things like that. You can create variables. And so let's assign the value 27 to the variable a, so a equals 27. So you assign the sort of scalar integer to a. You can also build vectors and matrices using square brackets. So if you want b to be a vector, in this case a row vector, you just open square brackets, type a bunch of numbers separated by white space, close the square bracket, suddenly you've got a vector on your hands. If you want to make a matrix, so C is a matrix, C equals, open square bracket, bunch of numbers, semicolon takes you to the next line. So you can do 1, 2, 3, semicolon, the next line will be 6, 9, 12, semicolon, next line is going to be 33, 66, 99, and you get this nice 3 by 3 matrix. And so this should also tell you how you can make a column vector, which instead of separating things by white space, you can separate by semicolon. And so every new element comes into a new line, and you can make a column vector. So just some sort of MATLAB tips. I'd advise you to use short descriptive names for your variables. So don't just call everything sort of I, J, K, A, B, C, because as you accumulate variables in your workspace, you'll lose track of what is what. You want to give them names that remind you what they are. So if you're analyzing a molecular simulation, you might use sort of box length, might be a variable name. It will give you the size of your box. And atoms might be the number of atoms in your simulation. And so giving them sort of smart names that they're not too long. Don't use ginormous names because then it's sort of a pain to type them. So it's got to be a happy medium. They all have to be less than 63 characters. They can't start with a number, and they can't be a keyword. And so these are the MATLAB keywords, which are sort of special words that are used in scripts or functions or the workspace to do things like if loops, global variables, case conditionals, switches, things like this. You can't call variables any of these names. And so I don't memorize these. MATLAB complains if I try and use them. And if I get confused as to why it complained, maybe I'd look up the keywords and see, oh, it's a keyword. So how do you call a function? And so we're going to call a function bar. And so bar is a built-in function to MATLAB. If you call a function that doesn't exist, MATLAB will complain. You can call a function that you've designed by navigating to a local directory and then just calling that function. And so you can call functions that you've made rather than came shipped with MATLAB. But the syntax is always the same. You just type the function name, open regular brackets, argument list, close the regular brackets, and hit enter, and that will execute the function. So this vector b that we made in the last slides, we're going to plus it in a bar chart. And so the function call to make a bar chart is just bar, and then the argument is b, and you should get a nice graphic pop up like this. So you're going to get your bar chart of vector b. So MATLAB typically has argument lists where some arguments are optional. And so if you look up the MATLAB documentation, which we'll get to in 1 second, typically they have one argument or two arguments which are mandatory for the function to run, and then a bunch of optional arguments that sort of control how the function runs. And so the only way to find out is to look in the documentation. So how would I write a function? And so you can go to the File New menu. So you go File New and make a function, or you can just type edit directly into the command prompt. So you could do edit your function name.m, and it will pop up the text file that contains that function. So if this is a built-in function, you will actually open up the built-in function that ships with MATLAB, and you can actually make changes to it. So I wouldn't recommend that you do that until you're a proficient user, and probably it will have read-only permissions, and so you won't actually be able to make any edits even if you wanted to. But the most useful way to use this is you navigate to your local directory, and then you can open up and start editing your functions. So actually a quick way to navigate to directories is if you go to the GUI and you grab a folder and you drag and drop it into the MATLAB terminal, the terminal will automatically sort of move to that directory. Or you can use the cd command, and so you can look up in the help how to use cd to change directory. Okay, so getting help. So similarly to bash, when we type man and then the function name, like man ls, you can type help and then the function name to get rapid help within MATLAB. So that gives you sort of the short version of the help. The longer version of the help is actually buried within the help menu. If you just go to help, it will open up this nice new window, and you can type function names in it, and it will tell you everything you could ever possibly need to know, plus a bunch of examples, which is actually what I find the most useful part of the documentation. It gives you examples of how to run the function, and then you can just adapt them for your own purposes. The documentation is excellent, and so quick and dirty help, just type help. The thing I use most often is to go to the help menu, or you can go to Google. Again, Google is your friend, and so you go to Google and Google for MATLAB bar. Typically, the first hit will actually be the online documentation from MATLAB, but then other people may have written stuff to help you, so that may be useful too. So not everything you'll ever need to do is within these lecture slides. And so I'm encouraging you to look at the help, use the internet to allow you to do things that these slides don't tell you about. So any questions on this basic MATLAB operation? Everybody's managed to open a MATLAB terminal and type things, all seems to be running okay. People can open the help. Okay, great. So let's run through a few sort of examples of how to actually use MATLAB to do some basic stuff. So let's start with some data visualization, because a large part of what you're going to be submitting for your project is make a plot of this, do a linear regression on that, and so then you have to submit those things as part of your project. And so data visualization is one of the most important tasks you can do with MATLAB. So let's run through some of the most common data visualization techniques. And to make things concrete, we're going to analyze this super synthetic example. It's in many ways a bad example, but that makes it in many ways a good example. As we will see, that there's no sort of strong correlations or deep things within this data. It's just a data set. It's just a dirty data set we're going to play with. So we're going to analyze the sigmas and the epsilons for a number of classical water potentials used in molecular dynamics simulation. So we're going to get to this, but I thought I should use an example that's sort of taken from later in the course. And so if you're familiar with the Leonard-Jones potential, it's the way that we talk about how atoms interact. The Leonard-Jones potential is parameterized by two variables, epsilon, which is the well depth, and sigma, which is sort of how far out the well is. And this is the form of the potential. And so different models for water come with different epsilons and sigmas. And so there's the FPC model, there's the TIP 4P model, there's the TIP 5P model, there's the FP2 model. They all come with different epsilons and sigmas. And so we're going to just use this data set of the epsilons and sigmas from a bunch of water models to sort of illustrate some plotting in MATLAB. So very synthetic example. So download water_models.csv from Compass. So CSV, if you're not familiar, just stands for comma separated values. Means the values in the file are separated by commas. That's exactly what you would expect. And so you can open it in Excel. Like we said, Excel is great for quick and dirty things like viewing a file. So you can open it in there. You could open it in Notepad if you preferred, and you'll see the following. And so the file just looks like this. There's a header line, which is the reference from where I got all this stuff, which is Loughborough University in the UK. They have a great site for water models. Then there's a space, so it's a blank line. Then there's some headers, the name of the model, sigma in angstroms, and epsilon in kilojoules per mole. And then there's all the data. So these are actually all the water models, their names, their sigmas, and their epsilon parameters. So this is what we're going to study. So does everybody have that file downloaded? Okay, great. So let's load the data. So how do you get data into MATLAB? So you can copy and paste it. And so if you want to open this in Notepad, you could open it up. You could write sigma equals in your MATLAB prompt, open your square brackets, and then feed MATLAB a bunch of values to make a vector. And so instead of using actually the semicolon, we're just going to type return, and it will take you to the next line in order to make this a column vector. So you could type these things one by one or copy and paste them one by one into MATLAB. And when you're done, you can close out the square brackets and hit enter. Whenever you finish a statement in MATLAB with a semicolon, it suppresses the output. And so it won't send anything to the terminal unless there's an error. So that can be very useful in scripts and functions when you just want to execute a bunch of stuff and have MATLAB be quiet. It can be useful to omit the semicolon when you're doing stuff in the terminal in order to check that your output actually came through as you expected. And so it depends on how verbose you want MATLAB to be. As a new user, maybe you want to miss this terminal semicolon just to check that everything's running okay. Okay, so that's sort of the dumb way of loading data. Here's the smart way of loading data. And so let's do this together. So these are the commands you would actually type. And so you navigate to the directory using MATLAB that your CSV file lives in. And so let me see if I can launch MATLAB. Okay, so my MATLAB is slowly launching. Okay, so my MATLAB's not booting because I've not got a decent internet connection. Okay, so you'll just have to trust me. And so let's navigate to that directory. So you'd open your MATLAB terminal. In your GUI, you would go to your directory where you saved water_models.csv. You would drag and drop that enclosing directory into the MATLAB terminal, and that would allow MATLAB to navigate to where your file is. So everybody able to do that okay? I think if you type ls into the MATLAB prompt, which is the bash command for list, it will actually list all the files that are available. And if you type pwd and hit enter, it'll tell you where you are, your location. You can also do cd in order to navigate directories, just as you would in bash. But by far, the quickest way to navigate is drag and drop. Okay, so now we're going to open the file. And so we're going to type into the MATLAB terminal. We're going to assign to this variable FID. So this file ID is equal to fopen. And so we're going to open a file. And this function call takes two arguments, your file name, and then how you actually want to treat the file. So we're going to give it the file name, and we're going to say we want this to be reading, and it's going to be text. So other things, it could be writing in binary, or reading and writing in binary. Usually you either have R key for an input file, and WT for an output file. So it just tells MATLAB what it should expect to do with this file. So this is going to assign a handle to the variable FID, and it's going to allow us to use this handle to read the contents of the file. So it's like we're giving MATLAB the coordinates of the file. The next thing we're going to do is import our data into this variable capital C equals text scan. This is a very important MATLAB function. It imports data from a file. And text scan you can look up in the help and see everything you could care to ever know about text scan. But basically, I always use it in the following way, which is to just give the file ID, the format string, the number of header lines to expect, and the delimiter to use. Okay, so let's run through that. So the FID was just the coordinates we opened up here, tells MATLAB where the file lives. The format string tells it what format to expect. And so %f means it should expect a string as its first variable. But actually %f means there's a string there, but I don't want you to read it. So the asterisk tells MATLAB that there is going to be a string as its first field, but don't bother importing it. We actually don't care about the string. All we care about the epsilons and the sigmas. The next field is going to be the sigma, and the next field is going to be the epsilon, and they're both floating point numbers. So let's go back to the file. So text scan is going to roll through this file one line at a time. It's going to see the string, but ignore it because we gave it the asterisk. Then it's going to import the sigma and import the epsilon as floating point variables. We tell it there's going to be 3 header lines, so you need to ignore the first 3 lines of the file. And the delimiter between the fields is going to be a comma. And so your fields are expected to be split by a comma. I think the default is a space. In this case, we're a CSV file, so it's going to be a comma. Okay, so then we're going to import epsilon and sigma one line at a time into this, what's going to turn out to be a matrix C. So then you can close your file, and then you can access all the sigmas as the first column of this cell matrix, and all the epsilons as the second column. Because we pulled in the sigmas as the first ones, and the epsilons as the second ones. And so if you type these, you're going to get a vector of sigmas and a vector of epsilons. Okay, so there's a lot going on here, but this is a very common thing to use, is to use text scan to pull data out of a file. So has everybody managed to run this, even if they don't fully understand what's actually happening? Yeah? So probably your FID is wrong. And so probably this line has screwed up somehow. So you need to make sure your file ID points to a legal file in the current directory usually. So everyone managed to get sort of a vector of sigmas and epsilons for the most part. Yeah. Okay, so we can come back to this if you're having some problems. But let's move on a little bit. So let's plot this data. So maybe that's the simplest thing you could conceive of doing, is to plot the data. And so the way you plot the data is to make a figure. And so a nice way to make a figure is to get the size of your screen you're currently operating on. So screen size equals get 0 screen size, and that just imports into MATLAB what size of screen you're working with, because it will change depending on what system. And then you can make a figure, an empty figure that's going to hold your data. So figure, position, and these are just some nice values for the position that makes a figure that sort of fills your screen. So that's a nice way to make a big figure. If you don't care about any of this and you just want to make a small figure, that's sort of the default, you just type figure. So you just type figure. So this command is going to give you a sort of default size figure that's ready to accept data. If you want to make one that sort of fills your screen very nicely, you need to do something a little fancier and actually give figure the arguments referring to your screen size. So whatever you prefer. I just wanted to give you the more complete one here so you have it as reference. Then plotting stuff. So the simplest MATLAB function I can think of is plot. And so plot, X, variables, Y, variables, and then formatting string. So this is sort of single apostrophes, so single quotation marks. R0 dash means plot them in red. Symbols are going to be circles, and I want you to connect them with a line. If you want to see all the possible variables you could pass to the plot command, go to MATLAB help. So this is just sort of the bare bones, the X, the Y, and how I want you to format. You might actually be able to get away with just X and Y, and we'll format them in some default ugly way. Okay, so you're going to get a nice figure. So has everyone managed to plot the data and make a figure? Anyone having difficulty with that? Okay, great. So you've made a nice figure. So now it exists only on your screen. How do you save it? So you can go to the menus. And so if you ever get stuck in MATLAB and you just don't know what the heck is going on, you can't make it do what you want, you can typically get to what you need to do through the GUI. And so you can just pull down these menus, save things, modify your plot in some way. Everything I'm going to show you is going to be command line based, because the ultimate goal is to put these things in scripts. And of course, you can't point and click in a script as soon as you use the command line. So if you were to generate this plot using a script, the way you save it is to use save as command, get current figure, the name of your figure, and the suffix. And so it's going to save it as myfigure.fig, and then it's going to save it as myfigure.jpg. So .fig is the internal MATLAB figure file type, so you can open it up and you'll get exactly the thing that appears on your screen right now. JPEG is obviously a JPEG, so that's something you can then drag and drop into a report or a presentation or something. And so that will save those things in your current working directory. Does everyone manage to save their figure? Okay, great. So I'm going to pick up the pace, start for the last 5 minutes to get through just a few of these. If you're interested in any of these particular things, I would recommend you try them at home and just execute these commands, see what happens. So let's make this plot look a little prettier. So you can change the font size, you can change the color. So this ugly gray background you can change to white. You can give it a Y label and an X label. There's actually a built-in interpreter, so you can get some Greek symbols by prefixing the name of the symbol in Greek with a backslash, so it will actually make a nice epsilon, make a nice sigma. If you start this word with a capital, it will make a capital epsilon and a sigma, so that's nice. You can change the X limits, so how wide the X-axes are, and the Y limits, how wide the Y-axes are. The tick marks and the tick labels, and so you can actually define down to very explicit control over where these ticks appear and what value appears next to the tick. And so you have sort of ultimate control over these plots, which is one of the reasons MATLAB is great. Of course, you can do these via the GUI, but this is a nice way to do it within a script. So I'm going to keep going. If you want to play with these commands, I would recommend that you do on your own time. Okay, so that would start with an XY plot. What if I wanted to make a scatter plot? And so the call is scatter, and so this makes a scatter plot. So I would type figure to make a brand new figure ready to accept my data. If you don't type figure, it will dump your plot into whatever figure currently exists. And so you can very easily overwrite existing figures, which you haven't saved, and then you then lose them forever. And so it's always nice to type figure before you actually make a plot. Okay, so you type figure, type scatter. This is a scatter plot, so you have your X, your Y, your symbol size, and then your heat map, so how you actually want to color the symbols. And then I want them to be filled. And so it's going to make a sigma epsilon scatter plot, and it's going to color them according to the value of epsilon. You can then ask for a color bar to go next to your scatter plot, and so you have the sigma, you have the epsilon, and the points are actually colored according to this color bar, according to the value of their epsilon. So it makes a very nice plot. X label, Y label, changing the background to white, and you should get something that looks pretty nice like this. So you could color them according to a third variable, which is why this could be useful. And so your third variable could be quality of water model. So how good is this water model, for example? So you have X data, Y data, and implicitly Z data through this color map. It's a very nice way of plotting three-dimensional data in a two-dimensional plot. Histograms, something we do all the time is make histograms. This comes through the hist command. So you're making a histogram. This is your data. We're making a histogram of sigma data, and these are my bins. So the bins are going to go from 3 to 4 in increments of 0.1. The output of this command is going to be the count in every bin and the bins themselves, which you can then pass to the bar command to make a nice bar plot. So pretty easy. Hist command does a histogram in just one line. Bar makes a plot of your histogram in just one line. It's very powerful. Excel would be a huge pain making this. You have to highlight data and select things from a menu. MATLAB does it very quickly and very efficiently. You can then clean up the plot to make it look nice, and you should get something that looks like this. So histogram, something we do all the time, very useful way to do it. So again, think of this as sort of a library of MATLAB codes. I don't want you to memorize these things, but I want you to know that, oh, hey, I need to make a histogram. I should look back in these slides, and it will tell me exactly how to do that. You can make histograms with two axes. Sort of look like this. And so we had the sigma histogram in the last plot, which was sort of the projection onto the sigma axis. Imagine you wanted to make a histogram in sort of two different variables and then plot it in the third variable. And so what we're going to do here is we're going to concatenate our data. And so cat command sticks vectors together or sticks matrices together into bigger constructs. And so imagine I have two vectors. I have my epsilon vector and I have my sigma vector, and I'm going to concatenate them along the second dimension. This is dimension 1 in MATLAB. This is dimension 2. If you have multidimensional 3s, you get other dimensions, so they would come out the board. So I want to concatenate these guys along the second dimension. so along this dimension, and stick them together into a matrix. And so then I'm going to end up with a matrix that looks like this. This is going to be data. This is going to be my epsilon values, and these are going to be my sigma values in a matrix. It's a very nice way of making matrices from vectors. I'm going to define my sigma bins, define my epsilon bins, stick the bins in this cell array, so don't worry too much about this. You can look up what the heck a cell array is just by looking up the MATLAB help, or you can just use this and not worry too much about it. And then you can do hist3 data and the bins. This is now going to generate you a two-dimensional histogram. And then you can clean up the plot by executing the following command. And so just think of this as sort of an idiom for generating a two-dimensional histogram. I think that's the easiest way to think about it. And if you want to delve in a little bit deeper as to what a cell array is, you can come and ask me, or you can look in the help. A scatter histogram. So instead of doing a three-dimensional histogram, you can maybe do a scatter plot with projections along each of the two axes to make histograms. So scatter hist. That might be something you're interested in doing. And then last slide for today, a surface plot. So imagine instead of a histogram, you actually want to make a surface plot. So you want X data, Y data, and Z data. So the Z data in this case is going to be the number of counts in your histogram, but it could be something else. It could be number of people in the world using that particular water model, or quality of the water model, or something like this. And so you just do hist3 to give you your counts and your bins. You put your bins into these vectors, which then go into this weird command called meshgrid, which basically just gives you your X, Y plane of points, and then you can plot them using surf. So you can do surf, X data, Y data, and your counts. And so this is sort of a weird command. I recommend you just try this at home. Look up meshgrid in the help. But basically, you're just defining a grid of X, Y points, and then you're plotting the surface height of those points. And you can make a plot using surf. You can also replace surf with mesh or mesh-C, and you'll get a slightly different plot. It will actually be transparent, so you can see through it, which can be useful sometimes. And the one thing I just want to warn you about is MATLAB is a huge pain in one regard, in that your X data is dimension 2 and your Y data is dimension 1. And so it's sort of permuted from what you would expect. You would expect X's to be 1 and Y's to be 2. It's the other way around. It makes for huge headaches. And so one of the headaches which you're immediately going to see is you need to take the transpose of your count matrix in order to make the X's and the Y's match up. If you were to type this without this apostrophe, MATLAB would complain and say your dimensions don't line up nicely. So the apostrophe sign takes the transpose of a matrix, and so it just lines up the X's and the Y's properly with the axes. So MATLAB gives you nice errors when something goes wrong, but just be aware of that. Okay, so just a very quick tour of some plotting functionality of MATLAB. I'd recommend you spend some time playing with these things. If you have questions, come and talk to me. Next time we're going to get into some MATLAB functions, actually using MATLAB to do some numerical analyses for us. So I think that'll do it for today. Do have a go at the project, particularly the bash stuff. Come and talk to me if you have problems with it. And next time we'll finish up MATLAB and give you all the MATLAB tools you need to complete the project. Okay, so I'll stick around in case there are any questions. Otherwise, see you guys on Thursday. And remember, this lab is available on Wednesday evenings for you to use. We've reserved it for you guys. I won't be here, but the lab is available. Great. Thanks, folks.